Hello. Good evening.
Good evening, sir.
Okay. So we are in week three of deep learning. This contains I think it is the most important week. So basics because it has this forward pass and backward pass of A and M, right? So back propagation is the backbone of the whole ML, right? So MLTL deep learning and thing. So mm, yep. Before I start, uh, is there any doubt? Uh, is there any doubt in week three? I mean, do you able to get it, or do you want me to take it?
Sir, can I ask?
Yes.
Sir, when we were in the first lecture of week three, in the feed-forward neural networks and learning parameters, uh, there was a statement that we choose an activation function so that if uh, the choice of activation function changes because the result could be say something like a survey out of 10 or out of 100, and the activation function could be like between 0 to 1 or upper bounded or something of that sort. So
Okay.
and also there was an example of how I think logistic function would be like between 0 to 1 and half, one in the negative axis of x of y and one in the positive axis, and it intersects y axis midway, and that's what. Sir, my only query was that if we take any function that gives 0 to 1, and then if we need like a larger upper bound, say 0 to 7, or NPS in a company which is 0 to 10 or something, can't we simply multiply with a larger number and then scale it? So why does how big the value has to be impact the choice of activation function?
Okay. Okay. I'll, uh, I'll explain that. Okay. Okay. Question. So, uh, see, activation function is something we apply after we do this linear multiplication, right? So weights. So first we have some weights, right? So let's say this is the input neuron. This is input, and this is like a hidden layer, something like that, right? So these are actually the sigmoid neurons. This is just just number, like from X you will get it, right? So X1 or X11, X12. So uh, and something like, so if you have three uh, like three columns, then that's how like the number will go. Okay. Uh, so uh, and this is the hidden layer which has two components. One is like you do the matrix multiplication with weights, right? So this weights, so it will get this as input, and they will be multiplied by something, right? So like weights, and you get a you call pre-activation layer. So this is called pre-activation. You get this, and on top of that you provide some function so that it we want something which is not linear, right? We want non-linear functions, like something like this. Otherwise it would have been just the linear function in some ways, right? Some addition of this, but uh, but we don't want that. We want non-linear function, so we apply some kind of activation. For example, if I apply a sigmoid, Uh, then this is one of the function. So this thing will give me from 0 to 1, right? So 0 to 1 will be the range of output of this. So all these neurons will produce output of very small numbers. Fine. So these are some tried activation functions, right? That sigmoid is there. Then later on ReLU or something like that will come. So ReLU will something like you give whatever you give, that thing you will get out, right? So basically y is equal to x if it is greater than 0. Okay. So greater than 0, then you'll get same thing. Uh, and more of this activation function will come up. But you can't have values which are very high number. The problem happens is this part. So what you have is one like summation of this w and x, right? So let's say this input is of 10, okay, 10 size. So let's say this are going to be 10, or this is going to be of 10, and then 10 weights will be required to multiply it, right? So this is for one sample, okay. So this is some number, let's say some, I would say a1, okay, some number you get a1, you can say. Now you will send another row, right? So next row, like x, this is x1, then you will send another row because you want to do for the whole data set, right? That is the idea. Now this is another row you send. So you will send it. So let's say you have 50,000 rows, right? So this summation will keep on adding after the batch. So it's called batch gradient descent. When you use batches, right? Or full gradient descent, you can say. Mini batch is something you can choose a small subset of this, and that way you can do. But you will realize that this sum is coming out to very high, okay, very high, like huge numbers. Even though if they are like in around like, so generally we prefer that all the values stays between 0 and 1. Uh, this is the uh, norm of the ML, right? So if values are between this of all the things, then actually we are able to compute things. Otherwise, it will blow the computer. It will not. You will not be able to carry, or you will not be able to store these values if you start doing this multiplication, then addition. So this multiplication with addition is very high. Okay, so if we start using something in range of 0 and 1, small thing, then multiplication and all will give you small values. So you can actually store them. Storing is also a problem, but nonetheless, like if very high values are there, then also like loss function, everything, it will be very tough, right? So you wanted to narrow it down to something. So that is why we need something like sigmoid. Okay. In ReLU and all, we have, I know that we have something like higher thing, more than that, but that will also, if you start looking at ReLU, you will realize that after back propagation or something, whatever coming inside is not very high, like it's not 7, 8, 9, that kind of values will not be there. Most values will be around 0 to 1. It might go more than 1 sometimes, like for ReLU kind of thing. Less than will not be an issue for that. So we need actually this, because otherwise these values will be very high. You will not be able to handle it. Okay, and machine will not be able to handle it. So we need this kind of activation function, which leads to first smaller values, and another is it's uh, we need non-linearity. So non-linearity is also achieved by this. Okay.
So what I understand is, so it should be a monotonously increasing function. Should not be like a sine function where the values repeat after some time, because then there will be confusion between two different values of input getting the same output. So it should be always an increasing function, but it should not be a linearly increasing function. It should be a curve, like, so that there's non-linear but continuously increasing within the particular range, so that when you give wx plus b as the input, and then
Mhm.
you do g of a, so it's suppose a is zero point 0.4, so the output is suppose 5, say zero point 0.6, whatever. The moment g is we do g of 5 0.5, as the g of a, the a value increases, the g of a should also increase. Or there should be two g of x should not be same for different values of a, because then they would.
Uh,
Or is it possible that g of a will be same for different values of a?
mm, no, I don't think that's possible. So whatever activation functions we are using, there it is different. So
So it is always increasing. Understood. I think since we are always putting the activation from the previous layer, so in a 100-layer network, we'll be doing activation of an activation of an activation. I think the first, I'm just guessing, I don't want to jump ahead of myself. But the point is, the care has been taken to ensure that the complexity of the function doesn't increase exponentially, but the systems do not get bogged down by the level of computation required for, because activation function happens exponential times now. So that is a ON kind of a function, and then the result should be between small numbers so that the computers don't get bogged down, and then
yeah,
you keep on doing that, and then of course, uh, it's very unique to see that they have taken log function, because the derivative becomes 1 by x. Again, derivative becomes 1 by x square. So it's again a monotonously decreasing function. It's like carefully derived way so that
yeah,
there is no divergence happening anywhere. There's
yeah,
convergence everywhere. And even the objective function, for example, if I am doing sample project on my own where I am taking, say, loss, I'm not trying to increase profit. I'm trying to reduce
mhm,
loss. That means
mhm,
that it's also so that there is always a end number which is zero. So there is not, the upper limit is not there. We never do profit maximization. We always do loss minimization. We always try to
yeah,
figure out the L function, not the P function. I think it's very, from what I, when I was reading the backpropagation, I thought it's very it's driven by convenience, and it works very well in that. If you structure a problem in a way that when you're trying to figure out a loss, and then anything that increases loss should go away. Then of course the gain will automatically increase. That's the way. That's how I understood. Maybe um, there is more as time passes. So just one final question. I know I'll not take everyone's time here. So I saw in the lecture that professor mentioned that the choice of function kept on changing, say from before sigmoid and then logistic sigmoid, and then of course relu and then leaky relu and so many stuff. So why did it take so much time to develop such simple functions which are non-linear, increasing, uh, like tan h or something? Why was it so difficult? Isn't it like very intuitive at present for us to know that just give me any function, let's create some function like x sin x or x e to power minus x sin x. Just create a complex function which can be computed easily using an FPGA or even because FPGA has been there for a very long time, even before the GPUs came. So you can
mhm.
program that one function so that it can keep on repeatedly doing it. Why
So
did, yeah. So yes, sir.
so I think when they started studying this thing, that time computation was not easily accessible. They had very difficulty with computing, right? So let's say even though sigmoid was a problem, they to first there is a problem that thing that it would have taken some time to understand that there is some issue with sigmoid. Now we should like use some other kind of function as well, like derivative is the since it is a all the like requirement of this like back propagation derivative should be the uh, backbone of this, right? So they maybe the relation was very late, something like that would have happened, and then they later on figured it out that okay, well, maybe we should go ahead with different kind of functions. So what could be that? So now once it appeared to them, they would have looked at something else, tried it, maybe it didn't work out, right? So that could have happened. And then what we are seeing now are the ones which actually worked. So we don't know what didn't work. I mean, I don't know at least. So this all are the things which actually work. So I don't think it's intuitive. When it is like the space is infinite, like you don't know the answer of it, then it is not intuitive. But now we know, so it looks like it's easy only.
Understood, sir. Because when I saw Professor's slide, just final point, sir. Professor mentioned that like a number, and then he mentioned like the final activation function. Then he mentioned the mean square error, which in school or in high school or in college we have been understanding that root mean square error, RMS error. It's taught in college, but now we are taught that take the binary cross entropy, and so that it becomes better than trying to optimize for the root mean square error. Some in physics, when you read about noise and heat and thermodynamics, we still go for we don't try to minimize entropy, we try to minimize the root mean square error. Similarly, it's true for so many other statistical functions when RMS reduction happens. So that jump from RMS, like creating the 0 to 1 version of a suppose 0 to infinite problem. I think that was the key difference. That's before the optimization could start. Is that's the reason why we moved from root mean square to binary cross entropy, and the same is true for softmax and stuff.
So we needed this probabilities, right? So the cross entropy, the reason behind cross entropy is you have this different, let's say four classes are there. Now you know that only four classes are possible, right? In your problem thing. So this is like y, true y. So this out of some four, one should be there. So we needed to convert this thing to probability, right? Otherwise, let's say if this number is 25, this is 30 and 12 and something like that, like 15, then it doesn't make much sense uh, in terms of like which class should I say. I know that this, let's say highest number, I choose that as a class, but it didn't, say that then these classes are not possible, right? Something like I'm not getting that kind of feel from here. So what we can do is we can change it to probabilities. So probabilities is a idea behind using this cross entropy. So now whatever this four are there, I'll just use like uh, softmax function. So basically, that is like e power something, but just think like we are doing this and then summation of it. It will give a ratio or something like that, right? So now this all values will be between 0 and 1, all of them.
Yeah, so because in college we have been taught ordinary least square method, OLS method. When you take
Mm,
25, 30, 12, 15, take an average. Maybe suppose 22. 22
mm,
minus 25 whole square, which is 9. 22 minus 30 whole square, it's 64. 22 minus 12 whole square, it's 100. 22 minus 15 whole square, it's 49. So moving from OLS and converting 25 to a probability OLS to be, so point is it's fantastic, but
yeah,
that's a hardcore method of getting large numbers, putting in calculator, and then getting to the part. But this is, I think, a faster way. So that change was what struck me as very say great innovation or improvement over OLS. Because still, if you go to college, entry level, people will teach you OLS, ordinary least square, curve fitting. Suppose you have to
yeah,
fit a line across this point, they'll not teach you cross entropy or probability. And final point was that suppose there are four models or four dataset pairs. So each of the probability of 25 happening could be different. Here we are assuming that 0.25, 0.25, 0.25, 0.25. Here the probability of 25 could be say 80% and rest could be like 0.33, 0.33, 0.33. So then you can multiply that as well with binary cross entropy. Take a weight and multiply it. That becomes very useful as well, which was not possible in ordinary least square methods and curve fitting. So that was pretty intuitive. The entire backpropagation looked very intuitive. The way it is designed in this chapter.
y-
Yeah,
yes, yes.
yeah,
It
yeah.
should be. That's how it
Yeah, but the
thought
point is,
process.
it strikes that it's. I know at present it looks so intuitive. Why didn't we think of it like 20 years ago? There was no rocket science stopping us from. Of course, we didn't have compute that time. We didn't have NVIDIA GPUs. We didn't have functions programmed
Mm,
into systems. But we did have like mainframe computers and supercomputers there. We could do a lot of computation. In fact, maybe
no,
the
it does look like, see, once you found the answer, then it looks like it was always easy. But if you start from scratch, let's say gravity, something is falling. Why is there? That was also not found for so many decades, right? So that that thing when found out, then okay, it's very simple. Gravity is there. Then I know something like very huge jump in physics, but that's okay. So if you have the answer, then you know it was easy. But if you never had it, then it was difficult. Like let's say zero was not there, then somebody invented zero. So how difficult was inventing zero? Still, I don't know how difficult it was, but now we are at least saying that we Aryabhatta invented zero. It has like changed the maths after it. So invention, I won't say that it was easy. It was always difficult. So now we have the answer, so we think that was easy.
Yes, I agree. So that was all the doubt I had. Like one was the choice of activation function, and then why like it looked like pretty one way of unique way of working: loss minimization, and then objective function, then loss function, then derivatives of gradient, which is partial, and then matrix multiplication, and then comes down to activation function, and then bias. So we can even control individual neurons. So that it looks very easy to be honest now, but um, yeah,
Yeah,
yeah.
it wasn't right. So first, when somebody use ML, machine learning, for that, like a few weights were there. To improve that, it was difficult. Then this deep learning was like after that, like way after that. So it's not that easy. It looks nice, but yes, it is. Now at least we can say that it's easy for us to understand.
I'm following the book Bishop mentioned in the curriculum here, Professor Bishop.
Okay.
Yeah. So there, in that Bishop book, the author talks about machine learning and then transfer learning. So that means if you have lesser number of sample sets to train your example, suppose, but you have say 1 million sample of English books, and but you only have 100 samples of what you want to train. So it talks
Hmm.
about machine learning and transfer learning. So, can you, if maybe in the end of the class, if we have some time, how does that machine learning and transfer learning, is it same as what we talk about RAG in transformer models when we change the weights based on the current small sample set? Or RAG is like fixed weight, only the input changes? Or the model weight also change?
Uh, so um, we we have few layers which we don't change. I think right in transfer learning, but what we do is we consider this as input. Now whatever comes out of this, so these are the weights which are trained by something, right? So let's say GPT was trained. These are the weights of this. Now you don't take the last layer of it, which produce the output, but you take this weights of that. Then you build your neural network kind of thing, or at least some kind of thing, and then you consider this as the the input to your network, and then you produce output. So this is the transfer learning, that weights which are learned by a lot of training. We use that and we'll utilize for our purpose. So this our purpose is, we can define here what we need, like network and all, can do anything. So it is. I think RAG is also kind of that. I'm not sure about.
Yeah, okay, sir. Thank you, sir.
Okay.
No,
Uh,
no, RAG is totally different, Naval. Sorry, who asked that question?
yeah,
Naval.
him only.
Uh,
Vasu,
no, no,
sir.
RAG. Yeah, sorry, RAG is different. See, RAG is about being context aware and how you store the retrieval, augmentation, and generation. Right. So it's basically how you store the information. It's stored as embeddings. Right. It's a frame. It's a way of thinking. It's a framework. It's not a model. Here, transfer learning and RAG are different. Transfer learning, like Manoj sir just explained, you take an established model. You could say, let's say you take ResNet, right? And you say that, okay, layer 4, it has 4 blocks, not 4 layers. It has 177 layers and it has 4 blocks, ResNet 50, right? Each block has multiple things. You can say that, block 4, uh, train weights true. If you say, it will open up, it will unlock those. And you retrain on your small sample, those weights will be changed. The rest is all you're exactly using as is. So that's transfer learning. Basically, you have learned something, you're transferring that here. If you want to train the last few layers, you can do that. That's what transfer learning is. RAG is more a way of storing data, retrieving data. You combine your own data with, let's say, you want to deploy a chatbot on your, let's say, all your office documents, right? You have to implement it through RAG, right? So it will first look at your office documents to retrieve some information. It doesn't have, then it may go online to retrieve some information, let's say. So that is RAG. In fact, I think the software engineering project, this term is has that RAG implementation also in it. It's a slightly different thing.
Yeah,
from to the best of my knowledge.
yeah, because what? Yeah, because suppose if you work for say at Infosys or Wipro and you ask to rank how many casual leave do I have, it will say 12. But if you go to Google and you ask how many casual leave I have, because a ChatGPT will not give an answer because it's not trained on the company's HR documents, for example. So my question is the weights that are in the model, which they are agnostic across the data being fed in, so the weights don't change, only how the weights multiply with the company's body of knowledge. So if I put the same model in say Hindustan Unilever and the employee asks how many casual leave I have, the answer would be 10. If I put the same model in Wipro and the employee asks how many casual leave I have, the answer would be 12. So the weights aren't changing. It's the X. So W is not changing, only the X is changing, or is the W also changing? That is what I'm
No,
saying. Is
there
this
there is
RAG learn or the RAG doesn't learn? It's a
there is
static.
no W. There is no W here.
Acha. Okay.
This is more about the information you're storing as embedding. Whatever information you store it in a certain way,
Hmm.
and then you can uh, query that database to get the information. How you query? You can use any model LLM to query that database, right?
Understood.
That you're not. So you're that is slightly different from the
There's no
transfer
learning
learning.
happening. I think we are going away from the agenda that professor that sir wants to teach. But maybe we'll take it on off from maybe
Yeah,
next.
there is no learning as such, right?
There's no weight. So learning is when the weight changes, the gradient and the weight
No,
updation.
no, no, no. There isn't. There
There's
isn't.
no weight updation happening in RAG.
No, 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 no.
Okay.
Not definitely not in the unless you're doing some really high end stuff.
Yeah.
Initial this thing, most people use LangChain and things like that and use it. They're all zero shot learnings. Like you just use it.
Yeah. So sorry, sir. Sorry for the a bit of,
Sorry, sir.
but it was like it was kind of intuitive that maybe we transfer learning, because the bishop talks about that deep learning and transfer learning. He talks about cancer skin photos in the first chapter. It says that they didn't have enough cancer photos, so they trained the model on all the photos, and then they gave it a subset of skin cancer photos, skin lesions. But so it became very popular. So even with a small sample set, and it gives a couple of example of transfer learning mixed with machine learning, and that gives the example that if you don't have large data sets, that train it on the general body, and then you train on a smaller set, it will work. That's the reason I thought maybe it's chapter one of Bishop. It's
Okay,
relevant to it. Thank you, sir.
okay. So maybe we can start. Okay, so like, is there any doubt related to back propagation or anything before I start? Like, uh, not
So
high level doubt,
the
but
loss
just
function, the loss function is del L by del W one part. Like if you can touch on that part, like that the math behind it. I was feeling a bit confused. In the last part of that sample question, it was like del L by del W two, del L by del W
okay,
three.
okay.
If you can
That we
touch
can do.
that part, that's the part. Yes, if you can.
Uh, um, so your your doubt is this first part, right? I will say
So
that.
the calculation, yeah. For example, in the sample assignment, they have given like three questions in the practice assignment calculations. I was, so how do we calculate it? Like in exam, if it comes, how do we? These formulas are pretty complex. How do we put that matrix and how do we multiply
Okay,
that?
okay,
That's
okay.
that's
I understood. So I think I need to start with the session, like, so that's where it would come. Okay. So okay, now so we'll take this example only, which is a practice assignment. Um, okay. I So what we have is first how to define this weights, right? What are these weights? So weights are defined like, how I think is, so layer. Then you write the neuron and then the number of inputs coming to it, right? So that number you give here. So maybe the weight neuron and then what you call actually the input or something, right? So let's say this is a hidden uh, uh, hidden neuron, and these are the input. Okay, you go like this. So this are going to be the input of this, right? So how will you write weights of this? Is like let's say this is first layer. So one layer, first neuron. So if another neuron is there in this, then you say two. But this is first neuron, and then the weight is coming on. So this is going to be 1 1 1. So if another weight I write, then that is going to be 1 1 2, right? So like this, and so we will have so on 1 1 3 and 1 1 4, like 1 1 3 1 1 4. So this is for the first neuron. If I wanted to write for the second one, then that is going to be 1 2 1 1 2 2 1 2 3 1 2 3 1 2 4. So these are the weights for all two of them. Okay, these are the weights for all. Okay? So this and so these are the network. It could be more neurons in a layer. So this is a hidden layer, and these are the weights representation to it. This is for now we can call as X, and it's also like H0 also, right? And this is like H1, um, first hidden layer or something, and we have this input. So so what we have is this hidden neuron, right? So first we do, let's say it's a sigmoid neuron, sigmoid or logistic uh, neuron, if logistic neuron. It could be later on we'll use different activation, but that is so first we do summation of W transpose X and plus we add a bias to it, and then whatever this value comes up, let's say if we call it as Z, Z is this, then uh, it goes like this. So Z is equal to summation of W transpose X plus B, and then we take like sigmoid of that, right? So minus Z, like so whatever the output we get is the output from neuron. So this W is the weight coming to it, right? So this W are all the weights coming to this um, neuron. Okay, so this is one neuron, and several neurons you can uh, have. So so this is a hidden layer, um, neuron and all. Now you could have multiple neurons and all. Now so at last you will reach at the final layer, right? So this is output layer. Okay, before it could be anything. Okay, any number of hidden layer you can choose, like hidden layers you can have as any number. Okay, I think more than one, then it makes sense. Mm, yeah. So final layer is softmax. So here there is a change in if we wanted to do classification. So classification we will use softmax. Otherwise, what we'll do is we'll not apply any kind of activation. We just let it be like just give it, right? So you can say um, if X goes in, X comes out, right? So no changes. Uh, Not X goes in, but we'll multiply with weight. Okay, will not apply any kind of function to it. Okay, things like so. Softmax is what happens in softmax is, let's say you get this vector. So after in last layer you will get this weight values, right? Some values. So like AL1, AL2, and let's say ALK, right? So you choose K classes, 3, 4, 5, that K number of classes, right? Uh, and that is like, so what you'll do is you first exponent it, e power AL1. The reason for using exponential is we wanted to have it as a positive and not negative, because probability exists in 0 to 1, right? The range is 0 to 1. If you have like exponential curve, I think that is like or that I think that like this. Okay, so I don't recall, but yeah. Now, so all the values will be more than zero only, if we use exponential. Then we what we'll do is we'll take summation of this thing, AL1 plus EL2 and so on till A e power AL. So this is just the first of that. So on, you will use same thing for all of them, right? E power ALK, and then this the whole summation, like this, whatever you get, same thing here, and you get this as output. So whatever you get this, it will be between 0 and 1, all of them, right? So that's why you can say these are the probabilities of it. So now we wanted to actually compare with this. This is what we call as y hat. So this is y hat, and we will have something as y, right? So this y we will have. Now we are going to compare with y. So generally, what happens is you get data set where y hat and y are sorry y is given to you as a value, right? So it's a, this many rows are there. Okay, the target of this is 0. So I'll say that class of set, right? So 0 is the target of it, or you get like um, 1 as a target, right? But now we are not going to use just a scalar value of it. We will convert this into vector. Okay. So let's say if it is 3 classes, total 3 classes are there, then I'll represent 0 as 1, 0, 0. So this is the 0th class is represented. Okay. First class I have to represent, that is going to be 0, 1, 0. This is first class. Now second class, basically 3 classes are there, so always start from 0. This is 0, 0, 1. Right? So this is like second class. So that's way I represent y. So y, you know that it's either going to be so this is like what called as um, I think it's represented as one hot vector. Okay. So EL or something. That's what the EL or one hot vector. That's where you will get as y. So like 0, 0, 1 something, it's second class. Now whatever probabilities we got here, we are going to compare with this, right? So this comparison will happen using cross entropy. So maybe binary cross entropy you are familiar with, but here we are using cross entropy. So that is like cross entropy is summation of like negative of y and then ln y hat l, right? So both of them like l, and l starts from, I think, so 0 to k.
Sir, isn't this Lagrange multiplier? Y log x log x, isn't that a Lagrange function? That's what Lagrange function is. Anyways, actually that converges. Sorry, sir.
Okay, okay, so this is cross entropy. Okay, and this is how you will compute. So you'll use all of the y's and then you will compute. So the good part about this is that at last we'll always have something represented like either this or this, right? Any number of classes you would have k classes, and any one is going to be uh, of say, one value. So rest of them will be zeros value. So if you do this, then YL is going to be, let's say if it is a second class, right? So first we'll multiply with 0, like ln y0 plus like 0 ln y1 and 1 and then like ln y2, right? So hat, so hats ln y hat 2, right? So this summation you will get negative of that. So these are going to be zeros, right? So we don't have to compute them. You can kind of ignore that. And one is also, we know that one multiplication one is also not enough. So what remains is, at last you will have always negative of ln y at some k, not k, but I think here L, right? Whatever class you got, that I'm representing as, and that you have to use as a loss. So this is going to be the loss, final loss of the thing. So this is for um, uh, we call it stochastic gradient descent. If you do this in stochastic gradient descent, we send one sample at a time. So one sample, then we back propagate it, then we send another sample, back propagate it. So this is what we call stochastic gradient descent. Um, but if you want, if you have more than one sample, like if you do in batches, then this function is a little different. Like you do it for the first sample, right? Then you do it for the second sample. You add all of them, like you add all of this individual losses, okay, smaller losses. You add them, then do the back propagation. But to just understand it easily, we are going to use stochastic gradient descent, and that's what being used in the course. Okay, that as the sir explains is the stochastic gradient descent. But if you had a bigger loss, that's also not an issue. Like summation of 2 3 points you have to do, and then you have to back propagate. Okay, just one change is there. Otherwise, back propagation, I think um, it doesn't change much. Okay? Uh, so values will be different, right, based on this whatever you got as individual losses. Uh, that you have to do. Now, so let's say this is the loss. Now we are going to do back propagation. So back propagation is uh, so the idea behind back propagation is so idea is that we wanted to update the weights. Okay, so weights and biases. Okay, so weights and biases we are going to update. So we wanted to have we'll use back propagation. So we'll use derivations. So we wanted to derive with respect to this only, right? So that how much I change, let's say some weight uh, with respect to loss, then how it will affect the loss, right? That's what this means. That how much I change in the weight, that will affect my loss. So if I have this back propagation like this um, derivation, then I can know that how much I change to have a change in the loss, right? So I wanted to reduce the loss and all, right? So something I have to use like let's say current weight minus some learning rate time gradient of loss with respect to weights, right? So this I'm going to and this gradient of loss I'll get from here. Okay. So if I do this, then I can kind of say that how much uh, change I'm doing and all. Okay. Uh, so this things we have to do. So let's say you had three weights and three biases. You have to take that many derivations. If you have nine weights, anything, so that number of derivations you have to do, right? So it's is it that um, we have matrices here, so we'll use matrix uh, uh, matrix derivation and all to make it easier for us. Okay. Uh, Otherwise, like individually also you can do, but that is like metrics we have, so we'll utilize that. So now what we have to do is we have to take the back propagation and derivation with respect to weight and bias. Just this you remember that we have to always do with weight and bias. But in between, like hidden layers and all come in the picture. But we the end goal is this. Okay, so we never have like dow L by dow H, and then what will I do with it? This is some hidden layer, like some use case do I have with this reality or something. So final goal is something like this. So this is our final goal. These are like internal requirement of it to achieve this all things, right? Now we let's say if I use a sigmoid function, logistic sigmoid, uh, then my uh, let's say uh, x I give, right? So 1 by should I just so let's do it for like 1 by 1 plus e power minus z. So z is you can say w transpose x plus b. Okay, plus okay. So this is that. Now, if you wanted to find the uh, derivative of this, right? So basically dow sigma by dow z. What is going there, right? So this part, if I want to do it, just this, then the formula is very easy. What I have to do is I have to take uh, sigma z and I have to multiply element wise 1 minus sigma z. Okay. So this part is clear, right? That how this formula is coming. If not, I would say that you can maybe refer to the lecture, but this is very easy. You can do that. Okay. That a derivation of this is this and this element wise multiplication. element wise. So we are going to use this also for our thing. Now, I what is there anything which requires? I don't think so. Anything else required. So what we do is we can take an example to maybe understand this how things are working. So let's say I have this weights. Um, so this is from the backpropagation PDF you would have gotten in like your supplementary section, right? So I'll cover that. Um, 1 1 1 1 1 1 0 0 1. Now 50 is 1 0 0 1 1. So these are the three weights. Biases are not given to us. Otherwise, they would have given us biases. So how many bias you expect for this? Like how many biases should be there for W1 if it was given?
Sir, one bias per neuron at the like middle, the hidden layer for the first layer, and then similar. So we'll add on the number of neurons.
So
If
what is the
the
number? Let's say for this W1, if I for this W1, whatever this weights are for any neuron hidden layer, how many biases you expect for that hidden layer?
maybe three, W transpose X plus B. So B would be the bias. So if B is changes across neuron, if not same across neuron, then three different B values maybe B1, B2, B3.
Yes. So three Bs we require some uh, uh, like, something like that. Right? So it's not given to us, and we are not supposed to update this also to get the correct answer. But otherwise, you would have gotten three weights, three biases for this, three for this, and three for this. Okay. You might wanted to update this also if uh, in like reality when you do the back propagation, when you write the code or something, train and model, then that time you will update biases also. Okay? Uh, so uh, now input is given to us. So let's say it's here, but input, so x is something like 101. This is my input, and y is also given, that's 001. Okay, so that means this is my second class. Okay, second class is the true class for this input. Okay, so these are input and output are mapped in there. So this x if I give, output should be second class. Okay, uh, now what I'll do is, so first we'll do so this is my, I would say, and finally I have three classes also. So this is my neuron uh, diagram, I would say, and these are the W1s. Okay? All of them, like not just this one, but like all of them. And these are W2s. Um, you get it. So this is W3, and finally we get here as y hat. Here we are going to give as x. So 1001 I would have given here. Okay, this will go, and some y hat will get. I'll compare with this 00. This guy I'll compare. Okay, so we call this as A1, and this is H1. Then here we have A2, H2. Here we have A3, and then we can call it as H3 also. But y hat is more easily or familiar that now. Okay, it's that is ending. So if you wanted to compare A1, I have to do 100 111 011, and then I have to multiply with. So what I'm doing is w uh, wx plus b. Okay, that's what I'm doing, and b is not there.
So in
Okay,
some places they teach us like W transpose X. So I was a bit confused where to take W or W transpose. But then I took W and got the result. So what's the difference? Some books they teach us W transpose X.
so the idea is it's it's like true that we should have taken W transpose X only, or something like that. This is the like then when we learn, we learn like this only. So
Yeah,
this like
because in the bishop book, sorry for interrupting you, sir. But in the bishop book, they say that like they declare that all W if they give, like in the example. So it's assumed that you have to do a transpose before you multiply, and they've like cleverly put couple of pitfalls when you do W X. They have kept that option as well. You'll get that wrong answer. If you do W transpose X, you'll get the right answer. So I
mm,
tried both to be honest in today's. Luckily, in our option, there was no trap that if you do WX, you'll get something, and W transpose X, you'll get something. But if that question comes in exam, if W transpose X plus B, the value is also there, say C, and WX plus B is in A, then you will get completely confused to be honest.
so the reason we are doing that is so we use like column as a this is like numerator and denominator kind of representation are there. Okay, so maybe you wanted to read about that, but we are using one of that, and in that we represent everything as columns. So let's say this is my input, right? I represent as column. That my input is a column. My y is also a column. So ideally, my weights should be column for one neuron, right? So, but what we are doing is we are actually taking them as a row, and transpose we are automatically doing it. You can say so. Whatever weights are given to you are transposed only, and then that's way given to you. Okay, that weights are represented as rows, and the why we are doing this because later on, like now we have this weights like this, right? But later on when you will do the programming and all, you will realize that you will randomly initialize this, right? So let's say you initialize first as let's say m cross n as weights, and then you have to for multiplication you do transpose of this, which will turn it to n cross m. It doesn't make sense. So initializes this way only, right? Just initializes this way with transpose, and you don't have to do it. So something like that is being used here. That we are not stuck with transpose. I think that's what Sir would have thought. I don't know why he did it, but that's what they thought. Uh, I believe that, and that's why we don't have to do transpose of anything. At least not while doing this multiplication. This W transpose is already done. Okay, you can think it that way.
So for the entire deep learning course, we assume that W is W transpose
Um,
till the end term.
um, yeah, I mean you can assume that weights are given whenever given is in a format as like W transpose. Yes, but you will realize that when we'll multiply in this later on, like in the hidden layers and all, we have to transpose this part. Like, but so they are not equal. I'm not saying they are. You consider both the same, but for you it's given in such a way that transpose you don't have to take. That
Okay,
fine.
sir.
Uh, so let's say this is weight uh, W X I'm doing, and there is no B. Otherwise, I would have added this B. Okay, 3 size would be 3. 3 cross 1, 3 cross 3, 3 cross 1. So how much? So what will be the output of this? What could be the size I am expecting? Size
3
of
by 1.
3 by 1, right? So you can this, and then addition will happen, but we have this as 0 or not there. Okay. Now input is I think 101. So I'll do the addition, and what I'll get is get 121. Okay, this is what I'll get. Now I'll do uh, I'll find h1. So h1 is sigmoid of a1. Uh, so basically I'll do sigma a11, um, sigma a12, and sigma a13. Okay. This is what I'm supposed to do, and these values are going to be like right 1 by 1 minus uh, 2 by 1 plus e minus 1, and the final output is 0.73, 0.88, and 0.73. This is easy, right? Understandable. I am referring to the PDF, but uh, this is the process. Okay. Now, since I have H1, so I'm here, okay, so this is H1. So H1 will become inputs to the next layer, okay. So what I'm going to do is repetition of what I did. I'll just, so this hidden layer, for this first hidden layer, the inputs were X, but for second layer, input is H1. If I have so here I third layer is output layer, but for that also input is H2. So now whatever I'm getting as output of this neurons are going to become input for the next layer. Okay, is it fine? So now I'll compute A2. So A2 will be like matrix, which is 1 1 1 1 1 1 0 0 1, and then I'll multiply 0.73, 0.88, 0.73. Right. So if you do that, you'll get output as um, 0.7. So first, if I do, then I have to sum all of them, which is 2.34. Then summation is 2.34 again. Then last one, okay, 0.7. So this is what I'll get as A2. Then I'll compute H2. Okay. Uh, Something like this. I will get output as 0.91, 0.91, 0.67. Okay, so this I got as H2. Then I'll compute A3. A3 is what I have as 0.91, 0.91, 0.67. I'll multiply with the weights. So weights are 1, 1, 1. So these are the weights. Now what I'll do is I'll do this matrix multiplication. And then 2.49. Then we'll find H3, or you can call as pi hat also. So that is going to be, I'll use softmax for that. It's a softmax over AT. So so what I have to do is I have to like exponent this 0.91 divide by this exponent of 0.91 plus 0.2.4, something like this for the first value, and I'll do this same thing for all three of them. So you get y hat is something like 0.15, 0.15, 0.70. Fine. Okay. I expect this much is fine. All these calculations. Um, so this is forward pass. We kind of did it like forward pass. Now we'll compute loss of after that, right? So now goes everything goes to the loss. So we did it. We'll use cross entropy. So I have y as 0 0 1. So what should I do as a loss? I will only take
Y minus Y hat.
y minus y hat. No,
That's error function. Okay, okay.
y minus y hat. No, not now, right? That's
Okay, okay.
y loss computation. So basically summation of uh, y ln y hat, negative of that, but you know that y1 y2 are 0, so I just have to do with y3, right? Y3 ln y hat 3. Fine, so that is 1, and ln of 0.7, negative of that. So negative of that. So if I do this, the answer is going to be 0.35. Fine. So this is my loss. Is it okay?
So is it L? This is loss. Okay, then you will get the del L by del W. Okay,
Yeah. So first I should know the loss, right? So
this is the
okay,
loss
this loss
one.
is there. Now I want to reduce it. So maybe it will be something lesser than that if I update the weights. Okay. So that is the idea, that I wanted to reduce this 0.35. It looks small, but because we use one example, but if you have multiple or something, it would be high.
Sir, sir, one question, sir. If you just scroll a little bit up the y hat that we calculated, so if we had kept the threshold for similarity, suppose we would have taken cosine similarity or some other similarity, and we had kept the threshold as 0.71, then the
Mm.
output will be 000 because it will all classify. It is classifying zero point 0.7 as 1 because maybe threshold will be less than zero point 0.7 for something to become from 0 to 1.
Okay.
If the threshold was higher, suppose it's 0.8 is the threshold, then the y hat will get categorized in a digital. If you categorize it below the threshold to be 0 or 1, it will all be triple zero. Is that a fair interpretation that how the threshold impacts the actual categorization of y hat into the values? Like the output can be yes or no. Suppose it's a question, yes or no, and the output is 0.15, 0.15, 0.7, then we have to put a threshold to select yes or no, 0 or 1. Isn't it? Or do we just keep this as like continuous real number,
Um,
decimal number?
so see, we wanted to say that this is the true class. Okay. This is one way of solving the question, that I will say this is true class. But on top of that, what we are saying is that this is not a true class. So that both the things we wanted to do it, and that's why we are using this
Yeah, so
caution.
the boundary is not a simple linear boundary like zero point 0.6 hard coded boundary. The boundary is an adaptive boundary. So,
Yes.
understood.
So if you do just that, then you will, maybe you have to use for two class only, right? You have multiple classes. You don't have two classes. So boundary will say that this is one class, this is another. Um, Maybe then multiple boundaries could be there, possibilities of that. Uh, I think it will be difficult, but this is a simple solution
Understood.
of it.
Understood.
Okay, so this is loss. Now we'll do. Uh, so we have uh, W1, W2, and W3. Right? These three weights are there. So this is from to first input to the hidden, then from second hidden, first hidden to second, and hidden second hidden to the last output. Okay, uh, like for the connection. Okay. Now, which weights should I update first, or which should I compute first?
Hello.
Derivative.
So usually it starts from the most outermost hidden layer, which is near the outermost layer, and then we keep on going back till the w x plus b, whether it's x is like the before the x becomes h, that comes the last. The first is the nearest to the output neuron. Maybe is that the correct understanding?
Okay, so yes, so we'll do the outermost is W3. Okay, uh, W3. Uh, you can do with like one element also. Um, that is also not an issue. But let's just see how we can do with matrices. It is quite interesting if I say. You can do it element wise. I don't know if you can always end up having a correct answer. I really don't know, because I always studied it this way, and I just wanted to show you also that way only. Um, Now what I'll do is, so loss with satisfied W3, right? So just think like uh, this is my uh, H2, and now whatever weights are there with respect to the final, right? So A3, let's say A3 here. So these are my weights, right? W3 weights, and from this I computed the loss. Okay, is it fine? So let's say this is loss. Now what I need to do to get here W3, right? So the chain of derivatives. So chain rule is going to come into picture. Then later on we'll, I think here also we'll have chain rule across multiple paths. So that will also, I think, come into picture. So which to with whom I should first take the derivations. What is contributing to loss? This is my loss. What is contributing to loss? If I change this, then loss will change.
Sir, the value of y3.
Okay, so y3, right? We can do. So if I do with respect to y3 only, then what will happen is I am restricting myself to this path. Fine, this path, this path I am going. Then so what I have to do is I have to maybe um, see what are the changes happening in this three uh, paths, right? Or basically W3 3 1, W3 3 2, W3 3 3. So this is one way of doing it. Another we can do is we can just go through all the paths. Okay, is it okay? So all the paths, but we know that these are going to be end up having zero, so it will not affect it, and that is also there. So instead of doing y3 only, we can do with respect to y the compute, and we know that y1 and y2 doesn't exist. So let's say if that value is not right, if I ask you what is the derivation of let's say x square with respect to y, if I ask you that, like d x square by dy or something, then you know this is going to be zero because like doesn't affect y, right? So whenever we have some variable which doesn't affect it, we say it as zero, derivation of that. So this is one where y is connected, or y hat uh, is so actually it is y hat. That is what affecting the loss, y hat. Here h3, you can say h3 also. Tau L by tau h3. Right? Now, what is affecting uh, y hat? What is that is connected to y hat? We wanted to reach to W3. Okay, so that is the path. What is affecting H3? Uh, what should I change to?
So I think W3 into H plus B will become A4. So so Y will again depend on the W3 and then same W2 then W1. That's where but they're all like multiplication and addition and then the activation function. So then I think it will
Uh,
depend on W3. Del Y by del
uh,
W3.
Not yet. I think. Okay, so the thing is, first my y hat, right, is affected by my A's A3, right? This A3 guy is affecting. We can see it. See,
Yes.
we got y3 here, and for y hat here, y hat to compute y hat, I required A3, right? You can see I
Yes.
use softmax of A3 to get this value. So A3 is actually affecting my y hat, right?
Yes, sir.
And then if I show you A3, right? So for A3, what is affecting them is W and X, H2. So W3 and H2. These two guys are affecting A3. Now, I'm do I care about H2 anyway? No, because I so basically there are two paths. Either you can go W3 way or H2 way, right? So you can think like that, but we don't want to go this way because we can find answer this way, the W3 way, right? So that's what we are going to do. A3 is affected by W3, fine. These
Okay, sir.
things are there. That that that's all. Like this is the easy thing. Now, see, I can prove what is. I can show you that what is derivation of this thing is. But these two things. Uh, if you do this, L by y hat. Okay, what do you expect? This loss by y hat derivation size. Like what do you expect size of it? Shape, physical shape. What do you expect the shape of it?
So it's three values of y hat. So each loss functions each loss compared to each of the expected output of. So it depends on the sample size. If it's three here, with
Mm,
three variables for each y hat one, y hat two, y hat three. So if
mm,
y hat changes, what is the so in common English, whenever the change is y hat, what is the impact on loss? So if the expectation changes, expected value of y changes, does the loss decrease, which is the ideal world we live in. So that is so three values will come here, I guess.
right. So you can say 3 cross 1. I mean some three y1. hat, y2 hat, y3 hat, right?
Yes.
Okay, so this how you'll get. Now, if you do this, y hat, which is a vector, and a3 is also a vector. So what do you expect dimension of a3?
So
This
A3 will be
yeah
very large because A3 is WX plus B. So or whatever W into WH plus B, because X becomes H in the following layers. So because the it's multiplying that with a larger vector, it would be like huge, like M cross X cross Y, very large. Not there wouldn't be any one cross thing. It will be very large vector.
okay. So this thing, if I tell you
Cross
this is
three,
going to be 3 cross 3.
3 cross 3, yeah. N cross N square the level of
It's
difficulty.
a 3 cross 3 because we have vector with 1. So what we do is we take yeah, y hat with respect to like a c1, then y hat with respect to a32, and then y hat with respect to a33, and so on. So this is for y1. Okay, y1. Then I'll do again with y2. Okay, a31, a32, and so on. So you'll get 3 cross 3. This I'm not doing it, but 3 cross 3. Now you wanted to multiply this. So that is like basically few of the tricks of this chain rule is the smartness that you wanted to multiply this. How will you do it? Okay, so you you can switch places of this matrix, right? So you know that this is the output you want, but how will you get it? You want to multiply this thing, right? So ideally what you want is you want let's say you want something like dl by d w3 1 uh, uh, in third layer neuron 1 right? Okay, something like this you want. So you actually want is y hat uh, or not this also. If I um, right, okay, fine, I can go with this way. So then I want y hat 1 with respect to a3. uh, which one will give me? I think it is this path, right? So I want a3 1 only. Then a3 1 is actually getting affected by w3 uh, 3 1 1, right? So this is what I wanted. Now your smart way that you get this matrix and you get this matrix. If you do it in matrix form, then how will you multiply it? Okay, so 3 cross 3, 3 cross 1. I think you have to switch it. Okay, you have to switch places. Then you can do the matrix multiplication. Otherwise, 3 cross 1 and 3 cross 3 is not possible. So if you switch it, let's say this way, and then you do the matrix multiplication, it's possible. So the switching and all will come later on also. So now when we'll do with W2, you will see the switching we do. Okay. So this is smartness of the matrix multiplication that you will require. Otherwise, it is like what we are doing is this only, but we require the switching. Okay. Now, okay. So now what we need is what is affecting A3. Okay. Now it is W3. Okay. Uh, so we can see here, this is A3, the W and H. Now, if I take with respect to H, A3, that's what. Uh, yeah. So what do you expect dimension of this A3 with respect to W3? A3, uh, yeah, with respect to W3, what do you expect dimension of this?
So the weights will be for individually for each of the neurons in the previous layer. So for each of these weight changes, how does that matrix change? So if there are like 3 cross 3 values of A, so here it's only one value, so 3 1 3 2 3 1 A32 A33. How does those three values? So just 3 by the entire weight, the dimension of weight 3. That will be 3 by 3, maybe 3 by 3 cross 3. The entire dimension of weight, like every element of weight, W3, and how change of that impacts the elements of A3, maybe.
Okay. So uh, so we have A3 as a vector and W3 as a matrix, right? So so if you do, it's like it will be difficult, but you will go with all the elements with respect to this, with one element first, then he'll go with second, and you get a tensor. Okay, you get
Yes.
this as a tensor.
Yes. Yes. Yes.
But to simplify this, there is a way to simplify this because we want one path of it. Okay, just one path where we don't get zero using this. Okay, using this like um, y3 ln y hat 3. We don't want to get uh, go all across the path which are zeros. Okay, so most of them are uh, going to be zero, and what you will end up having is uh, if you simplify it to make the computation simpler, they did it. So they realize what we can do, and you will also see it that you get is 1 cross 3. Okay, um, you should have gotten tensor, but you have to simplify that tensor. So this changes of dimension switching and all is the smartness of the computing. Otherwise, the matrix multiplication is happening, like if mathematics wise you go, then you have to do all the things. Okay, fine. So let's do it. So why I wrote this is, um, so if you go to, I think, and then now I show you here. Okay, so this is referred to AL. Okay, if you do with the last layer, so AL is the last layer. Okay, that's what it means. In our case, it is A3. Okay? A3. If you take this derivation, then what you get is EL minus y hat. Okay? You understood this part, like why how we are getting this?
Um, it was a bit complex, but yeah, I like kind of understood the last formula. So it's an exponential of L, I guess. I don't know.
E is one hot. It's not
One
exponent.
hot encoder. Yeah. Sorry.
Okay, so fine. So what it is trying to say is that you do tau L by tau A3 in our case, that take minus uh, of E L. L is the target, like which in our case is 3. Um, but make this kind of one hot vector, subtract it from the y hat. Okay, this is what it's saying. Now, if I write E3, how does it look like? 0, 0, 1, right? That's what it, I think, um, they use from, uh, I think they use, if you start indexing from 0, 0, then it should be E2. But you got it, right? So this is the way we can write the E2, and you will get it that this is actually the y itself, right? So if we look at the y, this is y, right? 0, 0, 1. So EL is actually y. So whenever you see EL in this, if you go back and see this lecture by sir, that wherever he used EL, you can write it as y on. Fine? Is it okay?
Yeah, so I think it's y1 minus y hat, which is like the misconfigured numbers. It becomes y1.
So yes, so now if you take this minus and you do this computation, you get y hat minus y. Fine.
Yes.
So this is with A3. So we kind of reached from here, right? So this path is covered. L, which is a y hat is A3. You don't have to actually do this part and this part. It's difficult. It's not that difficult, but you can maybe try it. Okay. So what is derivation of softmax with respect to input? This part actually you should maybe try it out. Okay. Softmax with input, you can maybe write a matrix and all, and then do it. But uh, I am not doing this. If you have doubt, you can ask me on Discord that I want to do it. I stuck up here. I will help you with that. So this is my uh, DL with respect to A3, which is y hat minus y. Now I just need one more component, which is tau A3 by tau W3, the matrix itself, right? So what it's going to be. So it's easy if we go to this part. Okay, so now we talk to the weights that here it's like Okay, in terms of our thing, computing with respect to parameters, okay, hidden layer and all, there are, I think it would have been at the back side, but um, so so just take it as, let's say we are doing with respect to W3. Okay, just all this value wherever you see K, you can think it as 3. Fine. Now we should have done that W3, and I'm doing that derivation. So yeah, so that I'm doing here, and what I get after this is I get uh, two kind of matrices. One is uh, simplification of it. One is this A K L theta, which we did. So A3 with respect to L theta, we did it. Right? So this computation we are done. This another part is HK minus 1 transpose. So basically H2, right? So whatever H2 is our case, like take K is 3, so H2 transpose. So H2 transpose we have to do, right? Why? Because this matrix multiplication will happen after using that. So to simplify this, we have done that. So this is going to be H2 transpose, right? So if we do it with respect to our problem, we get 0, 15, 0, 15, 0, 70, okay, 0.15, 0.15,
Sir,
point. Yes,
sir, can you continue next class?
sorry,
Can you continue next class?
in next class.
Yes, sir.
Uh, why is that?
And sir, it's 7 to 8 is the session. That's why.
Sorry,
7 to 8 is the session, so I need to pick my hostel food. That's why.
oh, are we supposed to have 1 hour? Mm, uh, next class, which is on, maybe you can watch it later, is it, if it's okay for you,
Okay, sir.
right? Um, so now we have y also, which is like this. So this two subtraction I'll do. I'll get some matrix. Then I have to multiply with H2 transpose. So what is my H2? I have to go back and check at H2, which is this, okay, 0.91, 0.61. So this is H2. I have to transpose of that. I have to take transpose of that. 0.91, 0.91, 0.67. Okay. So if you do this, what you will get is 0.15, 0.15 minus 0.3. And this is another matrix 0.91, 0.91. So this matrix multiplication, if you do, this is 3 cross 1, this is 1 cross 3, what you will get? 3 cross 3 matrix, correct?
Yeah, understood.
So this part is something,
Yeah, that S2 transpose was a bit confusing, to be honest. So there is
H2
something to be remembered, like del A3 by del W3, or because this del L by del A3 is pretty intuitive, that any delta between the expected value and true value is that is the so if expectation is same as the actual sample set, like the training data set which we have with the labels on, and the output expected output is same as the label, then we have got zero error. Then loss is immediately zero. So then del L by del A3 y hat minus y is very intuitive. That means if it is zero, that means you don't have any loss. We have modeled this either overfitting, or it's just like you are God or something. But yeah, the second part, the del A3 by del W3, the H2 transpose, that was,
mm,
I think, kind of a thing that was getting stuck at.
okay,
That's
okay. So first uh, I mean, we get this matrix kind, we get this tensor, but um, the idea is that if you write it here, if you can see here, think of it all K as 3, and if you will come across this part, right, that you do with respect to K1, um, and then you get HK1 as a
Yeah.
multiplication of it, right? So this is like we are reducing one dimension of tensor. So it should be 3D. Now we're converting it to 2D kind of thing. And this 2D part is something we are computing outside of it. So this part and this part now separated out. So that's why this is coming as a vector. Uh, don't
Yeah.
worry if you don't get it. The idea is that whenever you see this, solve this way. If you wanted to go deeper, maybe you give a thought about it, and you will be able to understand.
Yeah. So H is G of A and A is WX plus B. So that's how I understand. H
Yes.
transpose is that the G of A. So that means we are taking G of A, which is the activation function applied to the previous layer, each
Mm.
neuron. Then you got the value of the activation function. That's H. That's G of A. Then you transpose it and then you multiply it. So the previous activation function on the previous layer's weights previous layer's output is the transpose that is that value. Understood. S transpose.
Yes.
Understood.
So you have to take H2 transpose, right? Now I think little bit uh, simplicity we have. Now let's do with respect to if let's say you do with respect to B3 if
So
it
this
was
is a lot
there.
of computation and exams, sir. So they're like getting 3 by
Yes.
3 matrix in a calculator where in Excel we can do like really fast. So multiplying this
Yes.
isn't because of our exam calculator sometimes it just double clicks and goes away. But it's only one or two questions we can do. It's pretty scary that large number of 9 decimal points with like 2 decimal. Maybe we can have like couple of decimal points which looks similar and we can select that option and go on with it.
Yeah. So for quiz purpose, uh, uh, maybe you go across one path and then go do it because I think matrices will not be asked like just do the whole matrix, but element of that. So which element you want to do, you can go with that. But
Yeah.
but there might be mistakes. Uh, but otherwise, like you can go this way. Uh,
Yeah.
so now this is there with respect to B3. So if you would have done that, uh, you have to do with respect. Sorry, now loss with respect to first what is input to that y hat. Y hat is input to A3. Then A3 is actually being affected by this B3s. Okay, so this is going to be matrix, but right.
So, but
And
when the
this
bias is zero, so sorry for interrupting. When the B is zero, doesn't then this becomes like non-deterministic because B is in denominator and we are giving no bias initially. B zero is zero in the example, or do we have any bias?
we are not dividing, we are taking derivative. So
Understood. So if the change is bias, how does the loss change by the change in bias? Understood.
yes. Uh, so this remains same. Y hat y hat
Y
minus y
hat
hat.
minus Y,
Okay, and here you will get what you will get
the
with respect
transpose
to
function.
t. So what you will get is you will get 1 if there is a value. Okay, um, and I think this should there be one more? No, just one. Okay, you will get one only. Uh, so how I think uh, uh, is like let's say you have um, so what is going into hidden layer? Okay, like you can think in that way that if I would have hidden layer, maybe one, then like H11 H21 H2 H31, right? So this this should be the this will give you both, like this is bias and this are related to weights, right? Now we don't have this, so we just have one, uh, like thinking twice. So we'll get just one, okay, as a derivation of this. You can do it, but this is what you'll get. Uh, so maybe you can do this thing and you can transfer. Okay. Now something interesting comes up that what is with respect to W2. Okay. So this writing chain is important. That what you will have first is y hat. Nothing changes here also. Y hat with respect to A3 because that is the connection, right? So this connection is something we have to look into. So you can see we are at A3. Now where should I go? From A3 I have to reach H2, right? So how can I reach to H2? Um, so A3 has W and H2, W3 and H2. So I go along H2. Okay, so there are two paths or two kind of values are coming here to A3. One are W3 and H2. So I'll not go across this path, but this path, kind of like that. Okay, uh, not this, but this. So that's what I'll do. I will go with respect to H2. Then H2s are connected with A2, right? Then A2 is the one which is connected with W2. Okay, so this is how you get the chain, and this part we know y hat minus y, so we'll not do anything with it. Now something here changes that earlier we did with W3. Now we have to do the A3 again with H2 to go across this path. So what was A3? Uh,
A is WX plus B. So it will WH. A3 is W3H2 plus B.
yeah,
And
plus
the H is the gain function, the activation function. G. Yeah. W3H2 plus B
A3.
previous.
Yes. So if you do this derivation, so H2. So okay, let's say you have A311 something like I think it should be W31 summation of three things, but um, uh, how will I? Okay, just take example of like some other thing like you have W and X plus B, and this is something like called as Z. Okay. Now if I ask you tau Z by um, let's take it as H for simplicity. Tau Z by tau H. What is going to be the derivation using this? Just this
Only then W, because B
W,
will be
right?
zero, constant term.
Yeah. So for this also something like this happens, and we get derivation as W. But there is a catch here. The catch is you have to multiply it um, with this guy, and this is a vector 3 cross 1. This you got as a that's a 3 cross 3. Can you do the multiplication? No. So you have
The
to
transpose has to be taken, or the
you have
order
to
has to
take
be
here, and so W3, and there is one another catch is that you have to do transpose also. The reason is we do matrix multiply across multiple paths of the chain, right? So this multiple paths and all will come into picture. I think it was mentioned here, right? So this multiple paths we are going to see now. This path or could be that path, right? So that paths are affecting the uh, so I think here, right? So this you do, then what you will actually end up having it is uh, H with loss the here, right? So this guy, this is what we are talking about. W I plus one or whatever. So this a transpose of that and then multiply with that. Okay, so this is what we are doing now, and you can maybe refer this also that what is it transposes are there with respect to each of the element to get this derivation, and that's why we have this as a transpose. Now it is actually transpose. So whatever weight we wrote was W only. We are taking transpose of that. Okay, so we'll do that and multiply with this 3 cross 1 um, this part y hat minus y. Okay. Now this part is settled. So now we are here.
So usually matrix multiplication is not commutative, like AB is not equal to BA, but because you're using chain rule, we can cleverly put the chain of one before the other. But like we are taught in school and college, like A, B is not same as B into it.
Yeah. So
Then
that
just
is true.
yeah. Here we are using chain, so we can always put the chain one before the other. It does not make, if the output becomes like a scalar value, then it all converges. But if from the hardcore mathematics perspective, this looks like that matrix multiplication is not commutative. AB is not B.
Yeah. So AB is not BA, but yes, but for this we actually doing the smart way that we wanted to achieve this task. So the task is we wanted to do with one element, right? So how will you do it? The smartness is they use this transpose everything and then realize, okay, we can actually do this thing. So this all are tricks of backpropagation. We are of course we can't do commutative or something. It's not possible still, but the smartness is what led to this formula.
Yeah, yeah. Even when we are doing the simple matrix inversion, like 15 years ago when I was doing the sparse matrix, were a big problem. 100 by 100 matrix with a lot of sparsity in that. If you try to invert that matrix, it used to like bog down the computer. I'm talking about 2008, 2009 when I was working the very simple part. I think that's where the trick started coming, how to invert a sparse matrix and writing polynomial functions. So this looks very that way. If someone comes straight from college into this course, they'll get confused that why AB is becoming BA and something is again working. This the way like we were trained in ordinary least square method, like y minus y had square and like random ranges. Now we have like binary cross entropy and softmax. So it's everything is becoming standardized and normalized and like pretty coming into shape and form. This is pretty bit of not intuitive, but these tricks help in terms of long term value. Yeah.
Yes. So now we have this. So we already did this, right? H2 is sigmoid, and sigmoid with respect to input is sigma. So what we have is sigma z 1 minus this, right? So this part is that, and we have to take element wise multiplication. Okay. So we already did it for understanding purpose. Um, it um, was here or something. We do the we did it. I recall, but this is going to be the derivation of it. Okay, so this will get as a vector. So see, this is a matrix 3 cross 3. This is one sigma z 3 cross 1 subset from another. So ultimately, we'll get dimension as 3 cross 1. Fine. Now we do with respect to A2 with respect to W2. We have done A3 with respect to W3, right? So this thing we did, and we got H2 transpose. Now if I do with respect to W2 with respect to A2, what am I expecting?
So I guess intuitively H1 transpose like one step
Yes,
behind.
right. So H1 transpose is what we'll get, and it should be 1 cross 3 in our case because H is of 3 sides. So if you do all this matrix multiplication, which we can kind of do it. So W3 W3 is 1 0 0 1 1 1. W3 1 0 0 1 1 1. W3 transpose I have to take. So I think I didn't do that. I'll do the transpose of that. So let's write that 1 0 0 1. So this is W3 transpose. Okay. Earlier I wrote was W3. Now y hat minus y, it is 0.5
0.15, 0.15, 0.7,
minus 0.3.
minus
I
0.3.
just do it. Okay. So this is what it is. Now this should be element wise multiplication of both of them. Okay. Just I think I missed it, but this should be also matrix. So this is also another trick that you have to do it. Now, so before you do matrix element wise multiplication, remember that we need it as a vector, right? So 3 cross 1, 1 3 cross 1. If you do, then only you will get this vector. Then you can do matrix multiplication, element wise multiplication. So to do this, you should first multiply this. Otherwise, you will not get the correct answer. I think so. You will not get it. Maybe you multiply this, then do matrix multiplication. Could have worked. Uh, could have worked. But later on, like if you get another kind of dimensions, then it would not work. Let's say this was 3 cross 2 and this was 2 cross 1, something like that. So that kind of issues might happen, right? Um, so you'll get output as 3 cross 1 and then you can multiply with 3 cross 1. Um, so this thing will work element wise, but sorry, this element wise would have not worked if you mismatch this thing, right? So don't skip the step. First do this, then first do the matrix multiplication, then do the element wise. So that's what we are going to do. We have this. Now if I do matrix element wise multiplication, so first will be
First
0
will be 0, sir. 0.3. Yeah. Second will
and
be
minus
minus
0.3 minus 0.3.
0.3. Yes.
Okay, so this is what I got. Now I will have to make element wise multiplication. So sigma. Oh, sorry, I should have wrote, or I can write just h2 and 1 minus h2, right? That is
Yes.
what same thing. So if I go and check h2, that is 0.91, 0.91, 0.67. So that's what I have to do. 67. Now I will do 1 minus 0.91, 1 minus 0.91, 1 minus 0.67. So this is another uh, multiplication I have to do. So this also should be element wise, right? Uh, both will be element wise here and there. Um, so first I can say is going to be 0 because I do that. Another is something I will do. Maybe
It will be 0.3 into 0.09 into 0.91. It will be like big number. 0.27 in 27 into 91, 10 to the power minus 4, minus 5. Do one
about
calculator.
yeah,
27 into 91. It is 0.02457 and then like 0.0247. I think that's it.
okay, so I'm getting minus
0.0247?
minus 0.2
245.
0.02 uh,
47. 457.
yeah, I'm getting this,
Yeah.
and another is going to be
One third, so zero point 0.3, so it will be minus zero point 0.1, so minus 0.067.
yeah, so I'm getting 0.066.
67.
Let's not get this much. Maybe we'll go with 0.24
0.06.
0.67.
Yes.
So this is what I'm getting after doing this three things. Okay. Now I have to multiply with the H1 transpose. So H1 transpose is going to be, so H1 is column. Okay, remember all the things are column. I have to take it as a row. One, 3. So what is H1? H1 is 0.7388 and 7. H1 is 0.73, 0.88, 0.73. If you do this matrix multiplication, you will get 0, so 0, and right. Then we go across second path and you'll get
Point zero 0.07 minus 0.07.
minus,
0.07 minus 0.07.
is it 0.01 I should get.
Okay.
The why is that because the assignment, backpropagation assignment has this correct answer.
So this is 1 by 3 into, we are multiplying 1 by 3 into 3 by 1. So we'll get 1 by 1, no? No. We'll get 3 by 3. We're transposing it. Okay.
So,
Understood.
yeah, it should be like this 1 7 or something. So we are how do you do matrix multiplication of this? First we do this and this, then we go second. That's how we do,
Understood.
right? Matrix
Yes,
multiplication.
understood, understood. I was trying to find like, yeah, understood.
So this is what I'll get 0.017 or something. I'll just write this much, and this should be 0.02, 0.01. This is 0.04 minus 0.05 minus 0.04. This is the gradients I'm getting. Um, this
Yes,
is,
sir.
loss with respect to W2. Okay? Or sometimes you might see that theta. So this is what we got as a second part. Now comes the third, which is same as second. There is nothing changing here. So we have to do with respect to W3. If I would have done with W2, just so that you know that nothing would have changed. So I had with respect to A3 with respect to H2 with respect to
B2.
A2, then A2 with respect to
B2.
B2, right?
Yeah.
So this guy will be 1 only again, and
Yeah.
the rest of the changes. So I don't have to do this matrix multiplication. This whatever answer I'm getting here is the answer like this. Okay.
Correct.
So now we can do maybe with the W1. So let's write the chain. So this writing a chain is kind of I do because so that I understand it. You also get. Should I do with H2? Yes. There's
Yeah.
nothing
A3
changing
is
here.
A3 is WH plus B. H is again dependent on A2. A2 is again dependent on that thing. So yeah, it's like dependency function, one upon the other upon.
Yes. So that's why this chain rule.
Yeah.
And now what should I do with A2? With
A2 by W1, but then we know that uh,
we
WX
don't
plus B is
we have to do with this with H1.
H1. Yeah, H1 is WX plus B, and then H1
Then H1 with respect
H1
to
by W1.
uh, H1 with respect to A1.
Then A1 by W1.
A1 by W1. Okay, so this part. So in this whole process, what we have found out is this. I think till here we are clear.
Yeah.
That's what we got as a I think this value 0 minus 0.24. This is uh, uh, dou L by I can write A2, which is 0 minus 0.2 0.024 and minus.
0.067 minus 0.067.
So this is what is this much. Okay, clear. Now we are yet to figure out this three component only. So this three components, this H with respect to H1, what you will get A2 with respect to H1.
So so again, A is WX plus B, and then G of A is H. So here H1 is so del A2 by del H1 would be del W2 H1 plus B. It will be W2.
W2, right? So
Yeah.
now comes the trick part that we have to take transpose of it. Same as what we did here. Nothing is changing here. See, we already did this. There we had this much component as a you can say with respect to A3 we had del L by A3 you can consider. Then rest of the things are same. Three things we have to compute. So here we did W3 transpose. Now I'm going to W2 transpose. Then I'll do this part, and then I'll take X transpose, H0 transpose, right? So nothing is changing now. It's same thing. We are going to repeatedly do this. Okay. So W2 transpose, we'll say del L by del A2. Okay, whatever matrix I'm getting here. Um, I'll do matrix multiplication. Then I'll do element wise multiplication of uh, what now? H1 1 minus H1. Fine. Then last part is this. What will I expect as H0 transpose, or you can say X transpose.
Yeah. The input values that we gave into the model.
Yeah,
The raw
input,
input.
right? So four things. Now again you have to compute this thing. So if you write W2 as a transpose, that is going to be uh, 1 1 1 1.
So here, sir, just for the clarity, are you using the W that's given in the function, or are you transposing it? But that is very confusing, to be honest. Are you transposing
Which,
the W given, or are you taking it as it is?
no, I'm transposing it. So if you see W2 is 1, 1, 1, 1, 1,
Acha,
1,
you are
and
transposing here. Understood. Earlier we are not transposing.
here,
Understood,
here
sir.
it is
That's it.
W2 transpose.
Understood. Thank you, sir.
Okay. So yes, I'm transposing it. Now, now what will I do? So this, okay, this vector I know. This vector is 0 minus 0 0.024, 0 0.067. Okay, so this part I know.
Yeah.
Matrix multiplication I have to do. So I do that. It is minus 0.024, again minus 0.024. Then summation of this two is going to be
87 minus 0.087. 4 and 6, 7. So for 9.
uh,
So 9, 1. Yeah, correct. I thought it's 6, 3. No, no, 0.067.
uh, yes. So
Correct.
summation of this two is negative of this. So
Yes.
this thing I'll get. Now I have to take h1 and 1 minus h1. So what is h1? H1 is, so if you did all this thing, so you can come back and visit. So it's 0.7388.
73, 88, 73. 0.73, 0.88, 0.73. It's there, yeah.
So this part is 0.73, 0.88, 0.73.
Into
Just
0.27, into 0.12, into 0.27. Like 1 minus whatever.
by here I didn't got it. Yeah. So this part, then element wise multiplication 1 minus,
0.27, 0.12, and 0.27.
yeah, point, you can write it 0.27,
0.12, 0.27.
so this part, and then I have to take x transpose. I think it was 101.
Hmm. So we multiply x transpose first, or we first multiply this h into 1 minus h and then you multiply it?
So
Where does it trick
first,
come?
so now I think trick is not, but you should first do this part, like this element wise multiplication, then only do matrix
Okay.
multiplication.
Okay.
Okay. Uh, otherwise what will happen is this will give you 3 cross 1. Sorry, 3 cross 3.
Yeah.
Now how will you do element wise multiplication?
Yeah. That's the reason I was worried that it looks very big matrix.
Yeah, so you should not do this way. Uh, First you do this, so you'll get a vector and you multiply with the vector and you get 3 cross 3. So dimensions and all, you'll not make any mistake with the dimensions, right? That's why I said. Now, um, now what I do.
So now it's plain mathematics. I think then now I guess we can take ahead from here. It's like minus
Yeah,
104 into 0.73 plus that then
correct.
0.
So you can do that. The answer is minus 0.004, 0, minus 0.004, minus 0.000, minus, so 7. Right. So this is, I think it's understandable since both of them were 1 and this was 0. So you can see derivatives are kind of, both of them have same cross the maybe,
Yeah.
and
Yeah.
then 0. So so this is what you'll get as a final output. If it was with respect to B1, then again you have to same come do this whole thing A1 with respect to W1, right? So I'll just write it for you so that you y hat with respect to what A3, A3 with respect to H2, H2 with respect to A1, A1 with respect to, sorry, 8, A2.
H2 depends on A2, sir.
Yeah, so now A2 with respect to tau. Um, what does that affect?
A2 depends on H1.
H1. So yeah, we'll actually repeat this same thing here. And with respect to A1, now A1 is something which will be with respect to B1. Okay. So if you do with respect to B1, you will get 1. Okay. Just
because it's WX plus B, so
yeah.
then it becomes like WX goes away, del B by B, del B is 1. Yeah.
Yes. So yes. So it is going to be this way, and so answer should be like this 3 things only. Okay. So if you would have, we haven't done this matrix multiplication, that was like the vector you will get, right? That is going to be the answer for this.
Yeah, I think that's the last question in the practice assignment. This is the one, del L by del W1, which is like the most complex one because it
Yes.
depends on all. If we make one simple like calculation mistake in one, the entire thing goes for him.
Yes. So so actually this is dependent on no, see, the computation of del L by W1 is as simple as del L by del W2. If you have done correctly this part, right, which was required here, like um, this part del L by 2. So you will get this vector again. Then you have to do same thing, which we did here as well. Same thing we did, right? So 4. So you will always get this 4 vectors. You have to multiply them in some this way, right? So tricks are there, but you have to do that.
Yeah, that explains. I guess the mark should be in the same way. Like the del L by del W3, if we get like 3 marks, then del L by del W2 will get 4 marks. It just gets complex as you keep on going down.
Yes,
The del by del W1 is the most complex compared to the previous ones. Yes, sir.
correct.
Understood, sir. Thank you for that explanation. I guess it's like we went over by an hour, but it was very useful because backpropagation, at present, it looks intuitive because it's like everything fits in a place, but then it looks so intuitive that it looks like why people didn't think of it long ago because these partial derivatives have been there for 400 years. They are invented with calculus and long before, like Euler and Leibniz and others are invented. So it's not like something invented in 2000. It was invented in 16th century or 15th century. But yeah, I understood. It's very intuitive now when we see it. The matrix multiplication and then
Yes. So this 2 3 things you have to keep in mind. That first you should follow the chain. Remember that following chain is not enough. You have matrix like chain gradient across like multiple paths. So due to multiple paths, you have to use some tricks to get there. And there is like one more trick is you when you do A3 with respect to W3, you get a tensor kind of thing. So tensors and all, we don't want to go there. To easy or to simplify that computation, we do something so that we get finally a vector. Okay. So some computation wise we did it, and some required because we wanted to cross multiple paths. So that's why the matrix multiplication happens in some like different way. So 2 3 things you have to remember is that it's a del A by del A3 is always going to be, or AL last layer of this is going to be y hat minus y, right? And same like I think we used something like,
minus y hat. Yeah, same.
okay. So this is same thing. This one thing you have to remember for, let's say, maybe this purpose. Um, if you do with respect to, let's say, W3, then uh, del L by del AL and for A3, then with respect to this, you will get a vector. Okay, so vector you have to transpose it. Transposition of vector at the last layer. So last whatever uh, derivation comes up, del A by W, whatever are this, you always take transpose. Okay, this vector. Just remember, let's say your weight is 2 cross 4. Okay, weight vector. If your del L by del W is not coming as 2 cross 4, then you are making some mistake. Okay, some mistake is there, because what we'll use is, we'll use this W minus some learning rate of del W. Okay, so this thing we are going to, if they are not equals shape, then subtraction not happen. So just remember that if it is 2 cross 4, then it has to be 2 cross 4. Fine.
Yes, sir. Understood.
So the one thing, and let's say if you do with respect to any W2, so you can first with respect to, let's say, A3, so you'll get this vector. And A3 with respect to something you'll get, which, so first thing you have to do is you have to take a transpose of that thing. Like, um, yeah, then this vector you will get. So matrix you will get here, vector you will get here. So first you have to do matrix multiplication. Okay, don't skip this step. Then only you do element wise with this h2 into 1 minus h2, whatever you like this. Then you do this part,
And then
because
the H transpose finally.
then yes, finally this whatever h1 transpose or something, right? So never skip this steps, because you have to do this way. So for simplicity, you once again go through this. Okay, just look at this formulas given to you in this way. That's why I'm doing it this way. So I use this formulas only to come up. So like here you can see transpose was taken here. So this PDF explains how we are doing it. We did an example of it. That's all. Okay. So if you have an example with you, maybe it becomes easier. Right.
Yes, sir. So can you give us like couple of references where we can practice a bit more like this, because it will take couple of examples for us to, if you can post it on discourse or maybe in supplementary content, if you can try a couple of other examples with given solutions, because I saw
So
in Bishop they haven't given like I don't know which chapter this belongs to, but they haven't given numericals in Bishop. Bishop is like highly theoretical.
okay. Um, yeah, that is the issue with it. You will not find any questions or anything like this. Um, because later on, like they don't focus on too much on back propagation. The reason is they think whoever is learning this, they are not going to stuck up at back propagation. They do some better things, like build a
Yeah, I guess
model.
they have left back propagation to computers. They don't need humans to wrap their minds around
Yes.
as much. We just want to understand how it works, and then we can ignore it and move on. So that because we know if you want to know the nuts and bolts, we can always come back to. But we don't need to like do it on pen and paper in real
So
life after
so
passing.
I am actually I was actually working on one question. So I'll give you that. I'll create it, and maybe uh, 1 or 2 days I'll just write all the solution of it and give you it. So
So do
as
these
of
kind of questions come in gate as well, like these kind of calculations of propagation?
no, I
No, no.
don't, in gate deep learning is not there. So
Okay,
no,
okay. Understood.
gate DA doesn't have it. So
Okay, understood. If you can give us like one example, because for us it would be helpful if you can push it on Discord, because we can try a couple of numericals maybe just to drive home the concept of this H transpose on this one. Uh,
um
yeah. Then of
okay.
course the remaining part is pretty. I guess the next week four, which we couldn't touch today, but that's where the stochastic gradient descent, and then things will become really complex. If the fundamental is not clear, then it will become difficult when the layers increase or the activation functions change. That's the reason I wanted to solidify the foundation by practicing a couple of numericals, and then it becomes very easier. Just plug and play the different functions, activation functions, optimization, neuron layer changes, and write a code and it does everything for you. Yeah. That's the reason I was requesting maybe a couple of numericals.
Okay, yeah, no issues. So um what I'll okay. uh, so
So maybe it's very late. I guess we have gone over 2 hours to today, so we can. I know we are stretching your time as well, uh, but
yeah,
yeah, if you can put maybe somewhere we can. Yeah.
I think you and me are only there. Fine.
Oh, you have it handy? Okay.
No, I was showing you that I'm preparing this.
Acha.
You can
Okay.
maybe write this thing.
Okay.
as a question. Maybe you try it on yourself. I'll post
Okay.
this solution as a PDF or something. I'll post it uh, on like somewhere. Okay, so you'll get it. So,
Sure.
but this is the question I'm working on, which has different dimension of vectors like weights, not symmetric or uh, square matrices. I'm working
Hmm.
on non-square matrices. So if
Hmm.
you wanted to look into it,
Understood. Understood.
so you can try this question. I'll
Yeah.
I'll soon give it and
Sure, sir.
post it. Okay,
Sure, sir. Understood.
you can take a picture of this or
1 second.
uh,
Yes, yes. I was just trying to do that, to be honest. 1 second. Let me.
yeah, a screenshot of.
Yeah. Yeah. Yes, sir. I've taken it. Thank you, sir.
Okay, so right, so we'll do this and I'll update it. Okay, so you
Sure,
can
sir.
maybe find the answer.
Yeah,
If
yeah.
you wanted to do it, you can. If
Yeah,
you have
I'll do it
solved
and
it,
post it on. I'll put it on Discord. I'll
yeah,
solve it
that
on
that
Discord.
will also
I'll
work.
take the picture and then I'll put it on.
Yeah, so I know that what you did, you
Yes, sir.
made a mistake. I'll point it out.
Yes,
If
yes, yes.
it's correct, that's great.
Yes, sir. Understood.
Okay, so that's all for today's session. I'll maybe close this.
Yes, sir. So I just wanted to show one application that I have made. If you can, maybe once the recording is stopped, I'll show and I'll take some feedback. Um, if you have only a couple of minutes, I'll not take too much of time. So
Okay.